When we examine a petri dish, we are looking at clumps of around 1 million bacteria. When we zoom in here, you can almost make out one of these bacteria from the colony. If we look closer with an electron microscope, we can see the individual bacteriums more clearly. If we zoom in further, we get a size scale that is no longer visible by traditional microscopy, but artists can illustrate what goes on inside the cell. We see individual proteins, the membranes, and a flagella. If we zoom in yet further, we get to the atomic level in which molecules like proteins, DNAs, and metabolites all have very specific configurations of covalently and non-covalently associated atoms. The world is full of tiny balls, called atoms, and other fundamental particles like electrons and photons. It is not continuous. From physics, we know that atoms are themselves made of yet smaller balls, and in nuclear reactions, atoms can be split or joined and thereby change identity. However, at the energy levels that exist in the biological world, nuclear reactions do not occur, so you don't need to understand anything smaller than atoms. Think of atoms for the moment as billiard balls with weird magnets in various positions of their interior that make them interact with other billiard balls in geometrically defined ways. Those interactions come in two flavors in biology, covalent and non-covalent. The covalent type are really strong, and those are the ones that are made and broken during organic chemical reactions. The non-covalent ones are things like hydrogen bonds with much lower energies. In either case, you can describe graphs that capture the structure of aggregate particles within the cell. When we speak of the graph that results from covalent bonds between atoms, we call that a molecule. When we speak of the graph resulting from non-covalent interactions between molecules, we call that a complex. The remainder of what is happening in the cell is defined by the Schrödinger equation. This equation from quantum mechanics describes the energies and waveforms of the electrons surrounding the atoms. It describes the various states that the electrons will exist in. Chemical reactions involve changes to these electronic states and transitions of electrons between these states. The problem with Schrödinger is it turns out to be really difficult to solve. It can only be solved exactly for trivial systems like a hydrogen atom. It can be solved numerically, though it is computationally intensive, and physical organic chemists will often use such calculations to help them understand observed reactions that defy simpler explanations. However, simpler chemical theories such as VSEPR can explain the great majority of the chemical reactions that happen in biological systems. So we'll focus on this theory. The VSEPR theory is the one that deals with hybridization on the atoms. It is the theory whose consequences are physically encoded in the components of a chemical modeling kit, such as the plastic one shown here. To make a stable molecule, minimally all the holes in the pieces need a bond piece in them. Every end of the bond piece needs to attach to another atom piece. The simplest rule implied by these kits, that carbon likes 4 bonds, oxygen likes 2, nitrogen likes 3, and hydrogen likes 1, and so forth, are almost always true in the chemical reactions observed in biological systems. Additionally, this view of chemistry implies the existence of 2 types of bonds, sigma bonds and pi bonds. These bond patterns can be understood as pairings of orbitals between the 2 atoms. When a carbon, oxygen, or nitrogen atom exists in the sp2 hybridization state, it can use some of the available electrons to make double bonds. Everything else makes single bonds. Cell-based systems are essentially composed of the same atoms that the Milky Way galaxy is made out of, but are highly enriched for the atoms C, H, N, O, P, and S. Some common atoms like helium and neon are inert, so they play no role in biology. Others such as iron, magnesium, and chloride play major roles, but are not involved in forming covalent bonds. They are salts. For a chemical to be stable in water, it must be a pretty happy molecule. Water is a highly reactive chemical. Most of the synthetic organic chemistry used to make plastics and pharmaceuticals is carried out under water-free conditions because water is so reactive. So much of the diversity that can be generated in the chemistry lab is not accessible in biological systems because the required intermediates and reagents are not stable in water. For example, the Grignard reagent in chemistry contains a magnesium-carbon bond which reacts violently with water. It also does very interesting chemistry in the absence of water. So you can never have such bonds in a cell. As a result, the number of distinct bonding patterns in biochemical systems is fairly constrained, and the ones that make stable covalent bonds are largely limited to C, H, N, O, P, and S. Here I am filling out the grid of CHNOP and S, or SNOPs, carbon, hydrogen, nitrogen, phosphorus, or sulfur, crossed against SNOPs, and indicating whether that bonding combination is ever observed in biology. The gray ones mean they are super rare, but sometimes observed. You'll notice that at least half of these pairings are naturally observed, and to a first approximation, this plus the bonding patterns explains the bulk of the diversity observed in biology. Pretty much any naturally occurring chemical must obey these rules. There are some rare covalent bonds that do not show up on this list. For example, carbon-fluorine bonds can be generated biologically, but they are very rare in the biosphere. When something happens in a biological system, it is ultimately being implemented as many chemical reactions. That is the most obvious during the biosynthesis of chemicals, but it is also true when, say, you bend your arm. You're breaking oxygen phosphate bonds in many ATP molecules and modifying the structural state of the proteins within your muscle cells. So we need to understand what chemical reactions can occur. Chemical reactions define a change in the structure of participating molecules. There is a state to the atoms involved before the reaction, and there is a state when it is complete. The difference in energy between the two states is called the Gibbs free energy, and when it is negative, the reaction occurs spontaneously. During a chemical reaction, neither atoms nor electrons can be created nor destroyed. They are simply being rearranged. So the total count of atoms or electrons is conserved across the two sides of the equation. What happens under the arrow of the chemical reaction is not arbitrary. There are precise geometric events occurring on these molecules. The atoms don't just fall apart and rearrange, they must react through a constrained set of mechanisms such as nucleophilic substitution or elimination. In organic chemistry, the number of mechanisms available is fairly rich, primarily because transition metal complexes, these are things made with carbons bonded to atoms like palladium, they do fancier things. However, these molecules aren't stable in water, so there are very few mechanisms available to biological systems that involve metal centers. Because of all this, the number of reactions observed by biological systems is fairly restricted, and it generally falls under the categories of nucleophilic substitution, elimination reactions, or addition reactions. Reaction mechanisms can be represented visually using arrow pushing. The link here describes how it's done in more detail. Bond-breaking arrows originate on a bond and point to the atom that will receive the pair of electrons. Bond-making arrows initiate on a lone pair of electrons on one atom and point to the atom that they will become bonded to. Biochemists often use arrows in ways that don't actually mean arrow pushing. For example, here the scientist is showing the movement of a proton from an acid to a base. To draw this more accurately, the electrons on the base should be attacking the proton, and then the bond between the H and O should be broken with the electrons returning to the oxygen. In the product conjugate base, the electrons are not distributed across the entire hydroxide molecule as implied by the figure. They are localized to the oxygen atom. So the point here is to be a little careful in reading the diagrams you see in figures from the biological domain. Sometimes people use notations of organic chemistry loosely.